This is an abbreviated overview of acid deposition. The reduction of acid rain in the United States has been heralded as one of the great environmental achievements over the past several decades. In a 2011 report from the National Science and Technology Council, the opening letter to Congress reads, "This report concludes that the Title IX amendments to the 1990 Clean Air Act has successfully reduced emissions of sulfur dioxide and nitrous oxides from power generation." This report estimates the benefits and costs of complying with Title IX. The human health benefits of improved air quality are estimated to be in the range of $170 billion to $430 billion in the year 2010 alone. Substantial additional benefits result from improved visibility and improved ecological conditions. Later on, however, it says, despite these environmental improvements, research over the past several years indicates that recovery from the effects of acidification is not likely for many sensitive forest and aquatic ecosystems without additional decreases in acid deposition. Scientific publications and acid deposition models show that for sensitive regions, the sulfur dioxide and nitrous oxide emission reductions achieved under Title IX from power plants are insufficient to achieve full recovery to prevent further acidification. And now, more on acid deposition. The objective of this discussion is to gain an understanding of how human activities have physical, chemical, and biological consequences for the atmosphere. The learning objectives are to describe acid deposition and describe the effects of acid deposition on the environment. As part of the discussion, we'll be looking specifically at sulfur dioxide, nitrous oxides, the effects of acid deposition on the environment, the sources of acid deposition, and regional differences between acid deposition and the effect of the Clean Air Act. The production of acid rain includes the story of the interconnectivity of electricity generation, climate and weather patterns, and pollution. Acid rain is a problem that has largely affected the United States' eastern states. It began in the 1950s when Midwestern coal plants began spewing sulfur dioxides and nitrous oxides into the atmosphere, turning the clouds and the rainfall acidic. As acid rain falls, it affects everything that it touches. It leaches calcium from the soil, which can rob plants of important nutrients. The New England sugar maples have been one of the species that has been the most affected. Acid rain also can poison lakes in places like New York's Adirondack Mountains. Low pH waters can kill fish and has brought fish-eating birds to the brink of extinction. But how do these pollutants get from the Midwest to the eastern states? These fossil fuel power plants have installed large smokestacks to improve local air quality. However, the result is the release of sulfur dioxides and nitrous oxides higher up into the atmosphere, where they can combine with water vapor and move on prevailing weather patterns from one geography to the next. The formation of acid rain occurs through the following pathway. First, coal, which has sequestered sulfur compounds and nitrogen compounds, is combusted in a fossil fuel power plant and releases sulfur dioxide and nitrous oxides into the atmosphere. Once in the atmosphere, these pollutants can form secondary pollutants with the addition of water, oxygen, or other substances found in the atmosphere to form airborne sulfuric and nitric acid. Winds and weather patterns can move these acidic compounds across geographies and through the atmosphere over hundreds of miles. When the acid rain falls to the earth, it gets inside of the watershed and can infiltrate into the soil. According to the National Science Foundation, acid rain was first identified in North America at the Hubbard Brook Experimental Forest in the mid-1960s. As previously discussed, it is the result of long-range transport of sulfur dioxide and nitrogen oxides from power plants in the Midwestern United States. Hubbard Brook research influenced national and international acid rain policies, including the 1990 Clean Air Act amendments. Researchers at the Hubbard Brook have continued to study the effects of acid rain on forest growth and soil and stream chemistry. Long-term biogeochemical measurements, for example, have documented the decline in soil nutrients over the past 40 years. This loss is primarily related to the effects of acid rain and acid snow. Acid precipitation impacts forest ecosystem in the following ways. Trees at high altitudes are physically damaged by acidic fog and clouds. Once acid is in the soil and rain, acids alter the chemical processes that cycle nutrients in the environment and impact the ability of plants to acquire nutrients from the soil. Over time, forests that receive high amounts of acid precipitation experience cumulative negative effects, and trees experience a dieback, which influences the entire ecosystem. Beyond the effect of base nutrient depletion for plant species is a stress of the range of tolerance of all kinds of species for acidification. Though some species can tolerate acidic waters better than others, the interconnectivity of the ecosystem results in a change throughout the food system. Acid rain can also result in aluminum toxicity, making waters much more acidic. It results in the aluminum absorption from soil, which can be carried into lakes and streams, a combination which is poisonous to most aquatic species. As a final supplement to today's discussion, we'll be looking at control measures for acid deposition by exploring the effectiveness of the Clean Air Act on acid deposition through the podcast produced by the Department of Energy in 2017.